Okay, so I'm going to go ahead and talk about rotational inertia one more time. When I looked, there are a couple of new equations that they have on the equation sheet, so let's just kind of point those out. So I have here that sigma tau is equal to I alpha, which apparently is something we're supposed to know a little bit later, but they do have this new equation that states that I is equal to the sum of m I r I squared, which makes a little bit more sense with the way they're wanting us to do the problems. But this is a new equation that I have not seen before. So just kind of probably a more general equation instead of just talking about our traditional thing that we have on this page, which have all of the specifics here. So I'm not sure if they're not going to use these equations or what is going to happen, but for right now, we're going to go ahead and take a look at this equation as we go through. So moment of inertia is just going to be the sum of all of the different masses that are attached to something times the radius that they are away from that axis squared. So this actually makes it a little bit easier. And then we had talked about how the key concepts, and we did a little demonstration in class, the greater the moment of inertia, the more torque needed to produce the same angular acceleration. That's going to make sense. The more mass and radius that we are going to have, the more torque we're going to need to apply. The mass is further away from the axis, there's going to be a greater moment of inertia. And the ring has the greatest moment of inertia. This is a nice piece of information to know because a lot of times they'll give you comparisons. And then I don't think that you're actually supposed to have this yet. It's not that it's not a thing. It's just that it's going to be in the next section that we'll talk about once I return. All right. And then there's another thing here called the parallel axis theorem. This is another new thing that they're teaching this year. The parallel axis theorem uses the following equation to relate the rotational inertia of a rigid system about any axis that is parallel to an axis root center mass. So, and then they have this equation here. We have not used this equation in the past, so new to everyone. And I is just what that center, what the rotational inertia is at that center of mass place. So let's go ahead and go through. I'm skipping these two, and we're going to go ahead and do the examples. So we have three spheres with the mass indicated in the figure, and they're connected by rods of negligible mass, and we're just supposed to rate what is the moment of inertia of each of the rods. So when we would do this one here, we're taking a look at doing this new equation that they have for us, this delta m I r I squared. So for this one, for axis 1, it would go ahead and be the 2m times d squared plus m times 2d squared. So when we do this here, we would have 6md squared. That would be for axis 1. This is axis 1. For axis 2, and I'm just going to do this in a different color, I think. We would have same equation, the sum of mi ri squared. We would have md squared plus md squared, which would just be 2md squared. And then for axis 3, I'm going to put this back in purple because hopefully you can see, that doing this with axis 1 and axis 3 are going to be the same because these masses are distributed the same exact way, the same exact distance away. So axis 3 would also yield us I of 6md squared. Okay, so when we see that, it is very clear now that I1 and I3 are equal, and they are going to be more because they're 6 instead of 2 than I2, and that gives us answer choice B. And that's what we got. Perfect. Okay, which of the following claims about rotational inertia of a rigid object is true? And basically, they're referring to this new equation. I prime is equal to I center of mass plus RD squared. Was that what it was? RD squared? md squared. The d would be the r, right? It's md squared. And when we take a look at our answer choices, the first one says moving the rotational axis from the center of mass to another parallel axis will always increase the rotational inertia. This is the answer choice, but let's just talk about why it's the answer choice. So they're saying that the rotational inertia total, that I, would be whatever the center of mass is plus where that new axis is moved to. So you're always going to have that extra md squared because you're always going to have that center of mass axis rotational inertia. Here again, we have a uniformly dense cylinder that can rotate about any of the 4 axes shown. The cylinder has radius r and length L, where this r is much less than this length. About which axis does the cylinder have the greatest rotational inertia? So this is where we're going to be looking for the spot where the mass is furthest away from the axis. The further away it is from that axis of rotation, the more inertia there's going to be. So we have axis 1 has all of the mass over here. That seems like the most to me, but let's take a look. If we have axis 2, that's going to be very even. That's probably going to be your best. Axis 4 is very similar in that situation. And axis 3 is still going to be hard to do. Think about which one is going to be the hardest to rotate about that axis, and you're going to come up with axis 1 every time. Okay, cool. All right, this is the last one here. And again, this is going to be using that new equation. The symmetrical object shown in the figure has made a material with uniform density, and the object has mass 5 kilograms and length 4 meters. The object has rotational inertia 10 kilograms times meter squared about a vertical axis through its center of mass, which is indicated by the solid line in the figure. What would the rotational inertia of the object be about the vertical axis at the edge of the object? So what we're going to have here is we are going to have our I prime is equal to I center of mass plus md squared. So our I center of mass is 10. There we go, kilograms times meters squared. And then now we are going to be plus 5 times, and we're going to just go ahead and see where we are away from that. So that's going to be 4, whoopsie, I don't know why it stopped writing. There we go, 4 meters away, and we're going to go ahead and square that. So we have but we're only moving 2 meters away. We're only moving 2 meters away. So that's actually going to be a 2. So we have 5 from we were here, and we're moving 2 meters away from where we are. So our distance d would actually be 2, not 4. Okay, so we would have 5 times 2 squared, which would be 10 plus 5 times 4, which would be 10 plus 20, which is going to give us 30, which is answer choice C. Perfect. Okay, thank you for watching. Sorry, it's a little rough. I am in the car on my way to the airport. Bye.